So good afternoon, everyone, and welcome to the Southern Africa chapter of the Society for Conservation GIS webinar on understanding projections for ArcGIS. My name is Dr. Debbie Jewett, and I'm the co-chair of the Southern Africa chapter of SCGIS. I have been a member of the Society since 2012. And I first learned about GIS in 1994 when ArcInfo was one of the first Esri programs available. It was all code-based. I'm glad it's advanced now. But despite the changes in the versions of the Esri software and other GIS products over the years, the need for correct projections of one's data remains. It's really critically important to understand this concept. So this presentation will take the mystery out of coordinate systems, projections, and datums, and we'll start with an overview of coordinate system terminology and concepts, and then specifically discuss how these concepts and issues apply in GIS. This presentation is useful for anyone working with GIS or GPS and is especially useful for people who need to understand how to work with coordinate systems when projecting data in ArcGIS. So I would like to introduce you to your host today, John Schaeffer. John lives in the USA in Bend, Oregon. He's had to get up really early for today's presentation. So thank you, John, and I hope you have your coffee ready. John has been using and teaching GIS since 1992 with an emphasis on conservation and natural resource areas. He's also been volunteering with SCGIS since 2001, providing training and technical presentations at the SCGIS conferences in America. He's also been the lead instructor for the sASCGIS Scholars program from 2009 to 2018 and continues to stay involved in coordinating the Scholars program. John has taught GIS in over a dozen countries and including several classes in South Africa. So without further ado, I'd like to hand over to John to teach us about projections and coordinate systems. Please feel free to post questions in the chat and John will take them as they come up. Thank you, John.
Okay, let me click on share, make sure I've, okay. Excuse me, throat's a little scratchy this morning. So, like Debbie mentioned, I've been working with this quite a while, about as long as she has, maybe. And this presentation is about 30 years old. And I wrote it because I needed to understand how coordinate systems projections really work, especially in ArcGIS. Back then in 92, 93, there's a lot of theoretical discussion about coordinate systems and everything, but those discussions didn't help me figure out how to take data from here to here and basically, make everything work. So this is kind of, when I started this, and I keep updating it and everything, but I try to boil it down to just the essentials. So, oops. Okay, there we go. Presentation objectives. Understand basic concepts on coordinate systems for the GIS user. So terminology, what these terms really mean. Talk about geodesy, shape of the earth, geographic coordinate systems, datums, map projections, projected coordinate systems, working with projections in ArcGIS Pro, which is probably the more important part. Now, there's a lot of terms out there, some of which seem really confusing to me, but I boiled it down to 5 terms you really need to know. The first is geographic coordinate system. The Earth as a spheroid with location latitude and longitude with units in degrees. Projected coordinate system, the Earth or part of it flat with location in constant units. Datum, a large-scale reference grid based on a model of the Earth, and projection, a method of converting locations from one coordinate system to another. Sometimes we call that map projection. And then geographic transformation, a method to convert locations from one datum to another datum as part of a projection. So these are the key terms. So geographic coordinate system, latitude and longitude used to define the location of points on the surface of a sphere or spheroid. A geographic coordinate system is defined by a datum, prime meridian, and angular unit of measurement. Okay. A projected coordinate system, that's a reference system used to locate X, Y, and Z positions of point, line, or area features in 2 or 3 dimensions on a flat surface. Now, a projected coordinate system is defined by a geographic coordinate system. So realize you have to have that first, a map projection, any parameters needed by the map projection, and a linear unit of measure as opposed to an angular unit of measure. And in a projected coordinate system, all units are constant. Cartesian coordinate system. So this is a 2-dimensional planar coordinate system in which horizontal distance is measured along an x-axis and vertical distance measured along a y-axis. So basically, you've got your y-axis, your x-axis. You can locate any point by so far over, so far up. Now, the key to this is only in this upper right quadrant are both x and y values positive. That will come into play later on when we look at coordinate systems, okay? Datum. This can be a confusing term. I've tried to simplify it. It's the reference specifications of a measurement system, usually a model of the Earth. So we're much better at measuring the Earth than we were years and years and years ago. But still, we're not measuring every single little bump and tilt and everything else. So it's usually a model, okay? I consider datums as an established reference point to which coordinate systems are registered. So once we kind of get that model set, then we know where we can start putting our points. Datums are based on specific ellipsoids and often have the same name as ellipsoid. Now, an ellipsoid or spheroid took me a while to realize these are really the same word, okay? It's a 3-dimensional closed geometric shape, kind of like you see up here, all planar sections of which are circles or ellipses. So basically, if you slice through this spheroid, it's going to be an ellipse in most cases or a circle. And these are just different ways of measuring the shape of the Earth and impact both geographic coordinate systems using latitude, longitude, and projected coordinate systems. So I was doing mapping for forest fires in Oregon. Someone would come in with their with some GPS points, and I'd ask them, well, what coordinate system are you using? Because we used to have maps that were not all maps use WGIS 84 as their kind of global reference. You can actually have different geographic coordinate systems where the starting point is different. So even with geographic coordinate systems, you have to know what the underlying datum is. And also, of course, datums are different ways of measuring shape that are used in projected coordinate systems. So here's my note down here. Not all geographic coordinate systems measure degrees from same origin. And this can change based on the specific GCS. Almost always now, we're going to be talking about what we call WGIS 84 as our coordinate system. We're talking about geographic coordinate systems. But you have to realize there's hundreds of them of GCS, so geographic coordinate systems that exist. Now, there's 2 different types of datums. geocentric datum, horizontal geodetic datum based on an ellipsoid that has its origin at the Earth's center of mass. I'll give you a bunch of examples here. That's not really too important here. Geocentric datums are more compatible with GPS because the center of a geocentric data is, like it says, Earth-centered. And the satellites are pointing down towards your center, so that's why it's more compatible with GPS, excuse me. In local datum, horizontal geodetic datum based on an ellipsoid that has its origin on the surface of the Earth, such as North American datum 1927. It's one we used to use a lot around here. So here's a couple different examples. So here you see the shape of the Earth, more or less. The global ellipsoid, it's really centered in the Earth. And a local ellipsoid is kind of pushed up towards one edge. And here's another illustration here. And in this, the blue lines are Earth-centered. And like I mentioned before, it's centered on the globe or inside the globe, which is, in this case, the black line. A local datum is shoved up towards one part of the globe. So it works for this part of the globe, but not this part. It's way different, okay? So that's what they mean by local datum, okay? And they're still in use in a number of places. Now, projections, sometimes called map projection. This is a method by which the curved surface of the Earth is portrayed on a flat surface. And you can see there's some distortion, and we'll talk about that in a little bit. Next terminology, next term, geographic transformation, a system of systematic conversion of latitude and longitude values for a set of points from one geographic coordinate system, think datum, to equivalent values in another geographic coordinate system. So when you use the word, I'm going to project data, a lot of times it's going one coordinate system to another, but it also is often one geographic coordinate system or one datum to another datum. And we call that the datum shift. And if you're not using the correct transformation, then you're going to get something like this, where, well, this is what I really should have, and this is what I'm getting because I'm not using the correct geographic transformation between datums. And we'll show you how to determine which ones are best. Excuse me. So datums and geographic coordinate systems are often the same, and the terms are sometimes used interchangeably. So you can see here under coordinate system details, geographic coordinate system, WGIS 1984. Datum, D_WGIS 84. So essentially the same thing. And in ArcGIS, anytime you see a geographic coordinate system, think datum. Okay, that just helps me to not get confused about what this is. It's really, the datum that you're using, that model of the globe that you're trying to tie your data to. Excuse me. Get a glass of water. So I'm going to give you a lot of examples of the US, okay? Now, you need to understand that you will have a similar or parallel set of options. So I'm showing you 1, 2, 3, 4 different datums that I run into with my work. And because I know a little bit about these datums, and you don't need to worry about these particular details, you need to know the datums used in your areas and the details about them. So again, I will be using US examples, but just realize, where you're working, you're going to have several different coordinate systems, several different datums. Matter of fact, for this presentation, Debbie gave me two that they use. I got some data from Mervyn Latta, who I think is on here. And most of you probably know him. And he gave me some data that I used in a presentation. That was a third coordinate system. Okay. So what you need to do is kind of understand or know which coordinate systems, which datums are common in your area, and understand some of the data, some of the information about them. And I'll give you just an example here. So in Oregon, we used to use North American datum 1927, a long time. And it's based on the Clark ellipsoid. Okay, cool, whatever. But one time I got data from the U.S. Forest Service, and someone had listed the datum as Clark. And that name was not recognized by ArcGIS. But because I knew the Clark ellipsoid was the basis for the North American datum, what I was able to do with that data was basically put in North American datum 1927, where this other person had Clark ellipsoid and everything worked. So it's just a question of knowing the coordinate systems, the datums used in your area, and some information about them. So here's a few other examples of difference between NAD 27 and NAD 83. Western is about 100 meters. So if I bring in data and they're about 100 meters apart where they should be together, well, that automatically tells me in this case, well, one is in NAD 27, one is in NAD 83. And you can see a couple of the other examples here. So this is the type of stuff that you want to learn for your area that you're working in. Now, geodesy, study of the shape of the Earth. Earth was originally thought to be flat. Probably not really. I think the Greeks had it down and stuff. Later thought to be a sphere. So a sphere is a regular shape, okay, perfectly round. French geographers in the 1730s proved that the Earth is an ellipsoid or spheroid. And they did this by measuring a degree of latitude at the equator, starting out in Ecuador, which I happen to be with one of our SCGIS students. And they also measured a degree up, I think in Norway, far north. And they found that the length of the degree was different, which meant that it wasn't a perfect sphere, perfect circle, okay? So these are just different measurements of the flattening of the globe. Measuring the Earth in 3D, latitude, longitude. So, this is all pretty obvious, but I'll just go through the details. The key thing is measured in degrees, not in distance, okay? So obviously a degree here at the equator is really long versus degree here, okay? And the actual degree changes over different parts of the Earth. And even going up and down, because it's a spheroid, kind of flatter at the top than in the middle, then even a degree measured this way can be a little bit different. Now, location north-south is measured from the equator. And, being involved in GIS and geography, I have to go find the equator, this case, Kenya, this case, Uganda, this case, Ecuador, with another Debbie, okay? She was a scholar in I don't know. I remember all my scholars from the different years they were teaching, but we were able to visit Debbie in Ecuador. And then the location east to west is measured from prime meridian, and then which meets at the international date line, which is both 180 east and 180 west. So this is in Fiji. And sometimes you just need a lot of points to find the shape of the world. So I was lucky enough to teach a class in Cape Town in 2014 with Debbie and Fahima helping me. So it was a nice trip, nice place to be. Okay. So going from 3D to flat maps, distortion, impossible to flat a round object without distortion. So if you're in the old traditional geography class, they take an orange peel and peel it and press it down, and of course it gets squished. Pretty obvious. So when you are working with projections, there's four main types. Area, sometimes called equivalence. Shape, usually referred to as conformality. Direction or azimuthality, and distance. So when you're looking at the type of projection to use, you're looking at what's most important: area, shape, direction, distance. Direction. So if I was going to sail my boat, which I don't have, that would be hard to do. But if I was going to sail my boat from the west coast of the USA to the Hawaiian Islands, if my projection was not designed around direction, if my projection was not designed around direction, I could miss the Hawaiian Islands. Distance, same type of thing. I did a map. I used to keep track of my miles biking, and I did a map showing how far I biked in an imaginary way from my home in Oregon down to Mexico. And about halfway through, I said, well, maybe I should look at the projection I'm using. And it was conformality, I believe it was. I said, well, that's wrong. I should know better. So I changed it to a distance direction. And it looks like I lost 50 miles. So I just changed back. The heck with it. But you have to be aware of what characteristic you're trying to preserve, or which property is trying to preserve. Now, here's a few examples of going from 3D to flat maps. So this is the world as seen from space in 3D, projected onto a flat surface. And we can see a little bit of distortion here. Greenland looks really, really, really huge. South Africa is probably, well, all of Africa is probably smaller than it actually is. The world is seen from an Oregon perspective. So this is how I like to see the world. And what I mean, seen from an Oregon perspective. So this is Oregon, United States, so over on the Pacific coast. Here's California, here's Washington. But Oregon here on this projection, it's pretty true running east-west. It's kind of like what we're used to, okay? But of course, if everything is good for this part of the world, South America is getting really, well, I guess Brazil's making out. It's got a lot bigger here, but it's distorted. So basically, a projection goes and picks the area you're interested in, okay? You put your finger on the map and you push it flat, okay? So you're good, but then everything else is going to be distorted. And here's Indonesia. So we got Indonesia at the center, and everything else kind of radiates out from that. Kenya, okay. So this is in a UTM coordinate system. We'll talk about that later, where everything is kind of true along a north-south line. But as you move away from that, everything gets a little more distorted. As seen from France, I'm not sure why I picked France, but just showing you how each one of these is designed to make France look normal. I'm not quite sure what normal is all the time. And then everything else is going to be distorted. And Africa, Lambert, conformal, conic, South Africa. So I got this coordinate system from Mervyn when he gave me some data for a presentation. And then this is the Albers WGS 84 used for the National Vegetation Map that Debbie gave me that I use for some of the slides and stuff I'm working on here. So you can see it's all different projections, but each projection is designed for your area of interest. And it's just going to distort the rest of the world. That's just the way it is. Okay, so projections are created by transferring points on the Earth onto a flat surface. think of this as having a light in the middle of the Earth shining out onto projection surface. And where it hits is where that point kind of belongs, okay? There are three basic methods for this. Planar, it's projection surface laid flat against the Earth. Conic, this is a cone, kind of think of a dunce cap coming down over the surface of the Earth. Cylindrical, you're just wrapping a cylinder around the Earth. And where the projection surface touches the Earth is called the standard line. So here's a few examples. So this is a polar planar projection, and it's really only good for North Pole, South Pole, polar regions. This is a conic projection. So like I said, think of a dunce cap coming down over the globe. And in this illustration, everything is going to be good right here and right here, but not so good over here and not so good over here. So this would be where the standard line is in this particular tool. Cylindrical, this really isn't used very much as cylindrical. It only hits at the equator, so it's really only good for a small, swath of the Earth. But where a cylinder is used is here, something called transverse Mercator. We just take that cylinder, turn it sideways, and then the standard line is running north-south. And I don't see this, but I imagine there's no reason you couldn't tilt it a little bit one way or the other if you really wanted to. But generally, it's going to be have a central meridian running north-south. So this is going to be our standard line in this case. Okay. Now, developing a cylindrical projection. So basically, conceptually, what we're doing is we're taking a piece of paper, putting it around the globe some way, however we want to do it, and then be able to cut that piece of paper, lay it out, and then we'll have our map surface. And so one of my favorite projections is the origami projection. So you probably know this. Origami is a Japanese art of folding paper into different shapes like swans and stuff like that. Well, this is actually a joke. There's no origami projection. But the point is, any way that you can conceptually wrap a piece of paper around the globe, even if you have to cut the paper and then lay it flat, can be a method used for projections. Okay, let's get into a little bit of the distortion for projections. So conic projection, we talked about that, cutting through the Earth's surface at two parallels. And this is how a conic projection is used almost all the time. Instead of just hitting at one point, it hits at 2 points. And in most cases, this is showing really large part of the globe. In most cases, this might be just a little slice in here. So we have the Earth's surface curved. We've got our map surface. I've got standard parallel 1, standard parallel 2. And what we have here, excuse me, as an example of distortion, from A to B on the Earth's surface is quite long, but A to B on the map surface is shorter. If we get down to here, on the Earth's surface, C to D is short, but now we got distortion with C and D being longer, okay? So it's just a kind of a vision of how the distortion works, okay? And so when we design a coordinate system, we try to minimize that distortion. So let's go through. So I've wrapped my piece of paper however I wanted to around the globe. I projected points out. I flattened it. And then once we have reference points projected to a flat surface, then a coordinate system is established that provides a common reference on the ground. Usually based on Cartesian coordinate system, because projections are usually centered on the area of interest. So we have our north-south and our east-west axis. Where they meet is 0, 0. We initially designed a projection so this 0, 0 is in the center of our area of interest. And we'll show you a couple tricks about this 0, 0 later. So the coordinate system has a baseline running east-west, baseline running north-south, used to measure distance from the origin. So this is what I showed you before. The origin with a given value, and we'll talk about this again, of 0, 0 is where the baselines intersect. Location of any point can be described with two coordinates, the distance from the east-west and the distance from the north-south baseline. Usually referred to as XY, but sometimes as easting or northing. So instead of latitude and longitude, now we're saying XY or easting, northing. Or I suppose you could say westing and southing. I don't know. Come on. So I'm going to show you different coordinate systems used in the US. Again, remember, you have your own set of different coordinate systems you're working with, and you need to understand those so you can figure out any coordinate system problems. So in, excuse me. So in the US, we have something called state plane coordinate systems, one or more zones for each state. You might have the same in South Africa. KwaZulu-Natal may have one, may have two, depending on how big it is. Okay. Now, in the US, they're usually based on Lambert conic conformal for east-west trending states. So remember, the conic, that's the cone that comes down, place over the globe, and you've got a true line going east-west around the globe. So if something's longer east-west, like Oregon is, where I live, then we would use that Lambert conic conformal. And we use transverse Mercator for projection for states running north-south. So remember, transverse Mercator, take a cylinder, turn it on its side, and the true or the standard line runs north-south. So for example, Idaho is definitely a north-south trending state, okay? And so we would use a transverse Mercator projection. California, it's really trending north-south, but they just basically made a set of slices that are trending east-west, so they are using Lambert conic conformal. So again, it's kind of knowing what these terms mean to understand what makes sense for why we would use one, type of projection here and another type of projection here. Usually has a false easting or false northing. I'll show you an illustration in a minute. Units in the United States usually feet. You're so lucky you don't have to work with feet. We'll talk about that in a second. So I want to show you how this coordinate system works laid out flat on the map. So this is Oregon State Plane South. This jagged line here is actually county boundaries. So most states, well, all the states in the United States have smaller subdivisions called counties. You probably have something very similar in South Africa. And this shape here is just so that I don't have a county split by two different coordinate systems. So let's start here. We have a central meridian at 120.5 west. Okay, so this is basically the center east-west. We have the latitude of origin, and that's usually placed, at least in the northern hemisphere, usually placed below your area of interest. So I'm interested in this area. Here's my latitude of origin. And that's because, and it's placed below where I'm interested, because as I measure my coordinates going north, everything is positive. 0, 1, 2, 3, 4, 5, 6, 7, 8, whatever, okay? And we have a false northing of 0. Now, standard parallels. So standard parallel 1 is down here. Standard parallel 2 is up here. Again, think of that cone cutting through the earth at 2 points. Now, as you come away from the center, which is pretty obvious, you're getting distortion. So if I look at standard parallel 1 over here, hey, everything is good. I get out towards the coast and I'm getting a little bit off from my lines of latitude here, okay? And we can see that all the way along here. Now, false easting, 4,921,250 feet. Well, let me show you what's really happening there. This is my 0, 0. And this is the false easting moves 0 way over here. It seems a little strange to be halfway out in the Pacific Ocean, but I think when they designed this, they made it a lot different from an earlier version that had the 0, 0 about here, just so people would recognize by the numbers which coordinate system was which. But the whole purpose of this false easting is so that, let's go back a slide. So my false easting, if it was 0, as I move to the left, all my coordinates, my east-west coordinates would be negative over here. And they'd be positive over there. And that could be confusing. So the false easting basically, false easting and false northing, basically is just designed to put the real 0, 0 somewhere to the, in the northern hemisphere at least, lower left, slightly below your area of interest, or sometimes greatly below your area of interest. Okay, so we've seen this, and I'm going to do a little bit the same for Nevada, okay? So this is using transverse Mercator. We've got that nice north-south line. So our central meridian is 115 point yada, 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 okay? And we're just looking at this coordinate system here as a false easting of 200,000. So that means as I go to the west from my central meridian, okay, this is 200,000, 100,000, 0. So I don't hit any negative coordinates. Basically, that's all it's doing. And then false northing, 8 million. What? And I'll come back to this in a minute. And here is, this is the South Africa Albers WGIS 84 National Veg Map coordinate system that Debbie shared with me. And so I laid this out to show you how this works when you're laying that coordinate system flat. So let's look at some of the specifications. So projected coordinate system name, okay. False easting, false northing are 0, 0. So you have false northing, 0, 0. You're basically at the equator here, okay. Once coordinate systems I'm used to working with probably would have put the 0 down here, but you know, this is working. False easting means, you know, basically right here in the center. And what I noticed when I started playing with some data here is instead of calling out the coordinates like a minus as you're going west, it calls it out as yada yada west or yada yada east. So in this case, we're not worried about necessarily being on the, I'm going to say, quote unquote, negative side of our central meridian. Standard parallel 1 is 24 degrees below the equator. Okay, that's our latitude. That's also a latitude of origin. and standard parallel 2 is minus 33 degrees south of the equator. And notice that these standard parallels, they're a little bit inside your area of interest. Okay, obviously you're interested from here to here, but the standard parallels are a little bit inside, and I found that's pretty standard. And then the geographic coordinate system, WGSF, World Geodetic System, 1984, and datum, WGS 84, same thing. Okay. Now, here's, we're back in America, and believe it or not, there's over a dozen different type of feet. It's not just left foot, right foot, but you're so lucky to be working in a country that uses meters. But again, I want to show you how what seems like an insignificant detail can be magnified. Okay, so the two most common we use in the US are US feet, sometimes called US survey feet. So you already have a problem because a different name is used, slight different name, or international feet. So US service feet, and it's measured to the meter. So it's 0.1, 2, 3, 4, 5, 6, yada, yada, yada. So this is tens, hundreds, thousands, 10,000s, 100,000s, millions, 10 millions. If we come over here, basically you can see there's no difference until you get to the 10 millionth place, if I've calculated it right, okay? And you say, who cares? 10 millionth place? Well, let me show you. I care. So this is my house. If I measure the location of my dining room table in US feet, it sits here. If I measure it using international feet, it sits here, which is the bathroom. That's not really a good place for the dining room table. So just a little example of how something insignificant, okay, can make a difference. And I'm going to give you another example. So back to Nevada with its origin of 00 and its false northing of 8 million. So I was working with a company that was doing an environmental impact for a power line, basically running kind of north-south up in Nevada. And I was working with the GIS person in the office in Bend, Oregon, over here. They were getting data from the person in the field using GPS, and the data was coming in about 50 feet off. And I figured whether it's 50 feet north or 50 feet south, but it's pretty much north-south. And I look at all the specifications for the coordinate systems that we were using, try to look at all the details. And then I remembered we had this false northing of 8 million. And then I dug into the GPS settings, and the GPS settings had the name foot, but they really meant US survey feet or something like that. I forget exactly which one was different, but that little difference of some 10th millionth place, when you multiply by 8 million, makes a big difference. And so why I'm showing you all this is just the importance of understanding what these figures, values mean. If I hadn't realized this, I would have solved the problem. And so again, I think this is the third or fourth time I told you, you need to look at the coordinate systems and the datums that you're using, okay, that makes sense in your area, and get a understanding of some of the specifications. Okay, let's move on to UTM coordinate system. So the UTM divides the world into 66-degree wide slices. So this is used a lot for countries that are, or areas that are running north-south. So that's kind of like, you know, Nevada was basically, you know, it was put into a UTM zone, but the same concept because it was running north-south. often used by federal agencies in the United States. Units are usually meters. Based on that transverse Mercator projection, where I take that cylinder, just, turn it sideways. Usually has false northing, false easting, so all units are positive. So let me show you how it's kind of lined out here. So if you're in the northern hemisphere, you've got that slice, that 6-degree slice. So it's 6 degrees here, and it's also 6 degrees here, because remember, degrees are not constant, but as you go up, the degrees, the lines of longitude curve in. Okay, so we come down to here. Our false origin is 500,000 meters for basically our east-west, and it's no false northing for going north-south because we started 0. And 500,000 as the false easting just means that when I get over here, instead of having negative numbers on this side of the central meridian, it's all positive numbers, and it's going to decrease down towards 0 going this direction, and it's going to increase towards 1,000 going this direction, or 100,000, excuse me. And so here's a little hint. If you're looking at a coordinate on your map, and it's say about in the east-west coordinates about 200,000, well, then it's a little bit to the west of your central meridian. It kind of gives you an idea of where you might be located. Now, in the southern hemisphere, which is what you folks would deal with, okay, we do have the 500,000 false easting, excuse me, but we have a 10 million false northing, which basically makes your origin down here. And again, so all the values are positive as you work your way up. So that means no matter where we're at, both coordinates in a coordinate pair are going to be positive. So that's the general way these are designed. Now let's talk about UTM coordinate system on the equator. So this is Kenya over here. And I was using some data for a class over here, these two provinces, Narok, Kajiado. And I got data from Livestock Research Institute in Nairobi. And they give me the data, and here's the specifications. The projected coordinate system was ARC 1960 UTM zone 36 north. So I got this data almost 20 years ago. So they may be using something a little newer now, but this is what they're working with. Projection transverse Mercator, linear unit meters, false easting 500,000, that's standard for UTM. False northing 10 million. This is not standard for a north zone. Remember, north zone starts at the equator and works its way up. But they changed the coordinate system to have a false northing of 10 million, almost as if it was a southern hemisphere UTM, okay? Just so the values for your coordinate pairs are positive north-south and east-west, okay? And then you got central meridian, scale factor, yada, yada, yada. Coordinate system, datum, steroid, all this kind of stuff. But this is what I want to point out is that when you're working at the equator, sometimes you need to basically make a few changes, because if you're in UTM, normally this is 0, this is your equator, and values increase going up, values decrease into the negative zone, into negative values going south. But by changing your false northing and your false easting, you just make sure every coordinate pair has positive values. Okay? So hopefully you know enough, or you're starting to know enough about ellipsoids, projections, datums, coordinate systems to understand why some systems have been used, okay? You can better understand what is required when projecting data, okay, or why to use a particular projection, how to determine the parameters needed to project data from one system to another, key parameters to look for: coordinate system, projection, type of datum, type of spheroid, standard parallels and all standard meridians, central meridians, false easting, false northing, units. Okay, so if you start to understand how all of these pieces work to define a coordinate system, is that if you have problems, you can better understand what the problem might be. If you're deciding which coordinate system to use, you know, in most cases, you're going to use a coordinate system that's defined by your agency or whatever. But if you're starting a new project, you decide what coordinate system would be best, you can understand why one coordinate system might be better than another. Now, working with projections in ArcGIS. Excuse me, I'll get a scratchy throat here. ArcGIS Pro almost always works correctly between coordinate systems almost all the time. ArcGIS has gotten so good, I'll have some people say, well, I don't really need to worry about, you know, the coordinate systems because ArcGIS handles it so well. And in most cases it does, but you need to understand coordinate systems in case there are problems. And even though it appears your data is acting correctly, is more efficient and less likely to introduce error if all your data is in the same coordinate system, especially for analysis, okay? So if you got a couple background layers, you're not worried about them, they just need some background, okay. But anything you're doing with analysis, please get them all in the same coordinate system. So while ArcGIS can handle all of this, if you're doing some operation like a clip or a union, and data is in two different coordinate systems, before ArcGIS can do that clip, it's got to move these coordinates around to line them up. So that's a lot of math, and computers now can handle it compared to when I first started. And then it's got to do another set of complex math to perform that clip. So if you have everything in the same coordinate system, you're really just saving a step and less likely to have some error. Now, for this to work, ArcGIS needs to know the coordinate system of the data. So you can find it in projection files. So Debbie sent me a PRJ file with that Albers South Africa National Vegetation Map. Okay, all the specs. Oh, here it is right here. Okay. So I could look at all these specs and understand it and figure out what was going on. I could also import this particular file into ArcGIS if I wanted. If you have images like a JPEG or a TIFF image, they'll have world files. There might be some auxiliary files that help line up your data. Okay. Or it might be inside the GDB, geodatabase, if you're using a geodatabase, which I think hopefully is pretty standard now. You can find this, or you've be viewed in several places. You can go to catalog view, catalog pane, go to metadata spatial reference, or property source spatial reference to find out your extent, your spatial reference. Layers, properties, right-click on a layer, go to property source spatial reference. If you're working on your data frame, right-click, coordinate system, layers, details. So example over here, we see that we have some of the layers are in WGIS-84 and some of the layers are in Albert's WGIS-84, so for South American National Vegetation Map. Okay, so all of these are in there, okay? And you click on details to get all the specific details. So several places you can find what the coordinate system are. And remember that in a data frame, you can have multiple layers with each using multiple coordinate systems. But again, my recommendation is any of those layers being used for analysis should be in the same coordinate system. Okay, coordinate system dialog. So when you go in and you're going to work with coordinate systems, so I did right-click properties, coordinate systems. Now here it's telling me what my current coordinate system is. Over here, I have a spatial filter. And the spatial filter, you can specify an area, and I think you can just use like a layer, and ArcGIS will only list all the coordinate systems that it thinks applies to your area of interest. And so that can be handy. You can add in a coordinate system. So this is where I could have imported the PRJ file that Debbie gave me. Okay. It's going to show you the layers that are in the map. Okay. And if you want to have one of those coordinate systems added to your favorite, right click, say add to favorite, and it'll be listed up here. So this is really handy because then you don't have to keep switching and looking for your coordinate systems. You can also copy and modify, which I will show you how to do. You can save as a projection file. So if you've made a custom projection, I'm going to show you how to do that. You can save it as a .prj that you easy to share with other people. Now, there's a couple tools you can use when you're working with coordinate systems. So the coordinate system can be defined using the Define Projection Geoprocessing tool, okay? Now, this is very important. This tool is only used if there is no projection system defined and you know what the correct projection system is, or if the wrong projection system has been set for the data, okay? So define does not project the data to a different coordinate system. You're just giving it a different name for a coordinate system so that ArcGIS can interpret the values inside that map, inside the data, based on this particular coordinate system than the one that it had been named before, or the one that it had been mistakenly named or didn't even exist, okay? So be careful about using define. Realize that it's only telling ArcGIS, hey, this is the coordinate system you should use when you interpret the values inside the coordinate values inside that data. Now, the coordinate system can be changed using the project tool. And this is where you're changing from one coordinate system to another, okay? So important to understand the difference between defining and projecting. So again, defining just gives it a name, okay? A name of an existing coordinate system. So ArcGIS knows how to interpret the values. But projecting, okay, absolutely changes, it's going to create a new output in a different coordinate system, okay? And you can't do a project unless the correct coordinate system is already defined. I think that would be pretty obvious. Now, a few more things. Projecting data might also mean changing the data by using a specific transformation. So, going back to slide 4 or 5, geographic transformation. So that's where we're changing from one datum to another datum. That's called the geographic transformation. And it's not unusual for you to be working one coordinate system based on this datum, moving to another coordinate system based on this datum, okay? ArcGIS Pro provides transformation choices sorted by suitability for layers extent, mostly, but if you have a base map which covers the world and Pro always starts up with the base map unless you very specifically say no. That is one of the layers considered, and then ArcGIS might suggest a less accurate geographic transformation. Also, in some cases, you may need 2 or more transformations. So first you go from here to here, and then you go from here to here, things like this. And again, ArcGIS will give you these choices suited by what he thinks is best, okay? But how do you know which is best? Well, I've got a couple links, and I gave a PDF of this presentation to Debbie, so you'll have all these links in here. One is called Geographic Transformations PDF. I've been using this for 20 some years, and I did check. It's still available, okay? And then this is ArcGIS Pro's information on coordinate system and transformation topics, which is almost as good as mine. And now I want to show you how to use this Geographic Transformations PDF. Okay, so I was working over in Hawaii. This is one of the American states. It's about 3,000 miles off the West Coast. I'm working in the island of Hawaii, in the state of Hawaii. And so I'm going from Old Hawaiian, which is a datum used back then, a long time ago, to World Geographic System 1984. So basically, I've got some GPS data that's in WGS 84. I need to match it to Old Hawaiian or vice versa. And I'll look at these 2 options. And so the _1, _2, they have no meaning. It's just if there's 20 different variations, it'll be _1, _2, yada, 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 yada. But what I'm looking for is the option with the smallest box. So ideally, you want a box that just covers your area of interest. So if I look at option number 2, the minimum latitude is 18.88, same as option 1, okay? But if I go over here, maximum latitude is 20.33 versus 22.29. So that's probably running from here, just south of the island of Hawaii, to maybe about here, okay? So that's a smaller box than going, say, up to here. And then if I look at longitude, it's 156.1 compared to 160.3. So probably that's somewhere maybe about here versus somewhere over here. And then going over to 154.7, which is probably somewhere around here. So basically, this option gives me the smallest box, okay? And so that's what usually makes most sense. There's so many options. I'm sure that's not always going to be best, but it just makes a lot more sense if the area of my projection is close to the area of interest, you're going to have less distortion. If you can think about that cone cutting through the earth, if it's cutting through the earth way inside, versus just a little bit inside, I think you can visualize that a smaller box would give you a little more accurate data. Okay. Now, here's another place where I've got information about moving between different datums. And just as an example of not necessarily taking what seems to be most obvious, but implying a little bit of your own logic. So I was working on a project doing reef analysis, reef habitat analysis, way down in Mexico, down here, almost to the country of Belize. And so we had all these dive sites where we had our GPS collected in WGS 84, but all my land data was in NAD 27. So if I want to make sure everything lines up, then, I look at this list and I've got one option, underscore 18, that's for Mexico. Well, I'm in Mexico. Maybe I should use that. But then Mexico's pretty big. The center of that particular transformation might be somewhere over here. I'm working right over here, right next to Belize. I'm also working in a UTM zone, which remember, works better north-south. So I decided the particular option listed for Belize would make more sense than using this, okay? Now, I didn't test it out because we're taking the GPS for the dive sites on a boat that's kind of rocking back and forth, and it's like, I probably could have been, it probably would not have made any realistic difference. But the point is, now that I know how these things work, why not do it best, So I just want you to kind of realize, don't always necessarily take the obvious. Don't always take what ArcGIS gives you. Apply a little logic to your particular project, okay? Now, a few more things. So ArcGIS will project data on the fly. When you add data, it will give you a warning. So this will come up for maybe about 30 seconds, tell you it's doing a project on the fly. And this is very useful, but you have to know how it works. So, and it's almost a little bit like magic when this came out maybe 15 years ago. So anyways, but you have to know how it's working. So the coordinate system must be set for the data frame. In other words, if ArcGIS is going to bring the data in, it needs to know where it's going, what coordinate system's going. Transformation methods can be set if you know the specifics of the data added. So in a lot of cases, I already know stuff I've worked with before. I can make sure the transformation is already set. This works on raster data and images and vector data. It's really a nice way to project rasters. Project on the fly is not as mathematically rigorous as using the project tool. I forget exactly where I found this phrase in some documentation, but if you have the transformation set, if you know what you're doing, it's good. It's going to work good, but just a little warning. Okay, best procedure for highest accuracy, do all projections through the project tool, but I'm going to show you a little workaround when I do one of the demos. Now, modifying a projection in ArcGIS, so you can actually make your own projection. So I'm making the assumption that whoever set up the South Africa, excuse me, national vegetation map customized it. They started with something that made sense, and then they went on and basically changed it, okay? So I'm going to show you how to do that and basically to make it work for your data. Now, another thing is how to determine the coordinate system when there is no metadata. So you don't have any data. Well, you can bring data into an empty map and check some of the coordinate values. If you know typical values, they may help. So this again goes back to slide maybe about 15, where I say we have all these different coordinate systems used in my area of Oregon. And because I know a few things about those coordinate systems, then I know what's going on. So this, again, this is my house here. You can see how well my neighbor has irrigated his property versus mine. But if I look at the data here, 4,721,460.42. Well, once I see this 4 million, remember where I said that Oregon State Plain NAD 83 had a false easting of 4,900,000 or whatever. Then I know, oh, if I'm seeing this type of number, it has to be North American data 1983. If I see this number, then I know it's North American datum 1927 because the false easting is about I think it's about 1.5 million, something like that. Okay. And down at the bottom over here, I see 639 in my easting, but more important, I see 4,878,166.95 in my northing. And so I know this is a UTM zone. So remember, in a UTM in the northern hemisphere, 0 is the equator, and this is telling me I'm 4,878,166.95 meters north of the equator. We're just below 45 degrees latitude here. So if I know a little bit about common coordinate systems, this can give me a good clue. You can also check extents, go into properties, source for layer or metadata, and look at extents, and it gives you some coordinate numbers. But again, you have to have a sense of which coordinate numbers work for that area. Compare unknown data to a known reference layer. So I was doing another project in Mexico. It was architectural plans for development that we're trying to fight because it was going to take place near some turtle habitat. And the architect had the data in AutoCAD, computer-aided drafting, which I used to teach. And it gave me a UTM zone, but it didn't say which datum. But fortunately, I had an image that was in, again, I forget which one, it's probably in NAD 83. And one of the points on the architect's plans was the center of a bridge. So I could then basically compare it. And because the architect's plans did not, that the point on the center bridge was not on the center bridge, it's about 100 meters away, well, then I knew that he was working in UTM, North American Datum 27, versus UTM NAD 83. So then I was able to project his data to match the imagery and make everything work. So those are the few things that you can do to try and figure out where this data should be if it isn't. So I'm going to move over to ArcGIS and do a few demonstrations. So first one is I'm going to look at project on the fly and geographic transformations in an area in Oregon. Second, I'm going to go, what is the problem with this projection? So I was teaching a class for Jane Goodall Institute in Uganda. This person here is one of the SCGIS scholars from 2011, Philip, and he'd been fighting for 6 months trying to solve a projection problem, and I'll show you how we figured it out. And then I'm going to show you how to modify projections. So there's this person that always sends me very interesting coordinate system problems, which I learn a lot from. And so she needs to convert from geographic to projected to do some analysis. So I'm going to switch over to ArcGIS. Okay. So this is our first one. I'm going to work with AllNest. So I live over here in Bend, which is hidden by a panel showing who's here. And we're working over here on the Oregon coast. And let me go to map and bookmarks and go to owls. So here's the scenario. This is a course I did for the United States Forest Service 25 years ago. And what they have is they're working with spotted owl nests. Spotted owls are a threatened and endangered species, okay? And they need to be in old growth forest. So we wanted to be able to basically take the location of these nests, which in this case are fake. The Forest Service gave me fake locations, which is, good thing to do in this case. And then we basically, built a course around this. Now, the nests were actually taking in WGIS 84, or, that's how they faked it up. They used WGIS 84, World Geodetic System 1984. But all of the Forest Service data was in UTM NAD 27 Zone 10. So let's right-click on the data frame, go to Properties, go to Coordinate Systems, and we can see we're NAD 27 UTM Zone 10 North. Okay, so this is at that point in time, this is the Forest Service standard data. And this particular layer, there's only 2 layers in the map at this point, is using that coordinate system. There's also WGS 1984 Web Mercator coordinate system being used by my National Geographic base data. Okay? So what I want to do is I want to add in the original data that is in WGS 84. So I'm going to click on Add Data. And I'm going to go to Databases, Siuslaw. Siuslaw is the name of the forest. And I'm going to go to Siuslaw Data GDB, and I'll bring in WGS 84. And this is actually how we started the class. We had the students bring this in and then fix it. So I'll bring in my ALNES WGS 84 and I'll say, okay. And whoa, okay. I guess I had to refresh the base map here. I'm going to change the color to bright yellow so we can see. And so it looks like the WGS 84 data is lining up with the UTM 27 data. It looks pretty good. But I bet you can guess, if I zoom in, oops, not looking too good. Oops, looking pretty bad. Let's see if we can get any better. Nope, we're just getting worse. So let's measure. So I'm going to measure my distance. Planar metric, because the UTM zone here is they're using meters. And so I'm going to measure from the UTM NAD 27 to the WGS 84, and it's 8 meters. Shucks. I think I told you that in my area, Western United States, the difference between WGS 84 and NAD 27, North American Datum 27, is about 100 meters. But now it's only showing 8 meters. Well, let's see what happened. So I'm going to go back to my ALNES data frame, right-click, Properties, Coordinate System, but I'm going to check Transformation. So ArcGIS, I forgot to show you this before, but this was set to nothing. ArcGIS automatically calculated what it thought was its best coordinate, best geographic transformation. But obviously, that's not the best because I'm off by 8 meters. Okay, and this is a situation where ArcGIS is also making use of the base map in order to determine what the best transformation map is. So let's go back to Properties again. Let's just try this, and we'll go say, do not transform. We'll say, okay. And let's zoom out a little bit. There we are. So now we have the WGS 84 point. It's actually in a different direction, but let's go and measure the distance. And now it's 98.07. Okay. So now it's about what I would have expected. Okay. So let's go back, fix the coordinate system, the transformation, excuse me. And because going through that geographic transformation PDF file that I showed you, I know that this one, NAD 27 to WGS 84, option 6 is best for this area. I'll click OK. And everything is lining up perfect. And I'll zoom in really tight. Still good. And trust me, you can zoom in and you're not going to find any real difference at all. I mean, it just, you know, maybe a tiny bit of difference. So I know this particular transformation works. So let's go back to bookmarks, owls, and you can see they all line up well, okay? Now let me show you a couple more things. I'm going to turn off my OwlNest WGS84. I'm going to open up OwlNest TXT. Open, okay. So this is the file downloaded from the GPS, or as it would have been if downloaded from the GPS if these wasn't faked. And it's just like owl number 1 is active, owl number 5 is a failed nest, etc. Now, we've got a really nice tool, XY table to point, because a lot of times in the old days, maybe even now, it's not unusual to download your GPS data into some type of a table. And I'll use my XY table to point tool. And it's thinking. I think my computer's getting a little lazy this morning. And my input is going to be my owlnest.txt. We'll take all the defaults, okay, and we'll, okay, I got to move this out of the way, and I'll click on Run. Oops. I think I screwed up. I forgot to hit environments. Oh, no. So the output was NAD27 UTM zone 10. So I should have checked this environments to tell what output coordinate system I want. Okay. So let's go take a look at this. I'll close my table. Let's make these points bright yellow. And if I zoom in, you know, they're all good. So once your coordinates, once your transformations are set, okay, anything that involves the transformation, like this XY table to point tool, honors that, okay? Now, let me show you one more trick. So let me turn off this. I'll turn on our OwlNest, and I'll just, yeah, we'll just leave these. Okay, so actually, yeah, okay, we should leave this. Okay, so I'm going to go right-click property, go to source, coordinate system, or spatial reference coordinate system. And we're in WGS 1984, okay? So even though in the map, they're showing up as if they're in, you know, UTM NAD27, they are still WGS 84. So I'll say, okay. So I'm going to go right-click, data, export features. So I'll just take the defaults here. I'll check on environments. And it defaults to NAD27 UTM zone 10. And I'll say, go back to, and I'll say, okay. So basically what I'm saying is export this data to NAD27. And I'll say, okay. And we'll come in and let's turn on our original OwlNest. And now we can see that they're lining up. Our export features are lining up, okay? And if I right-click properties, source, go to spatial reference, it's now NAD27 UTM zone 10. So basically, I performed a projection just by bringing my data in, making sure I had the correct transformation, making sure it lined up, and then exporting it and exporting it into the coordinate system for my data frame. And I do this all the time when I'm developing a project. My first layer is usually some type of boundary layer. It might be a state, country, whatever for my area of interest. And as I bring in data and I play with the geographic transformation, once I make sure I've got it lined up, I can bring the data in, I can clip it, I can select it, yada, yada, yada. And then I can right click, data, export data. And basically, I am exporting and projecting at the same time. Okay, so real easy way to build up data for your projects. Okay, let's move on to the next map, Uganda. And so the issue here is these are all the different districts in Uganda. And my friend Philip had data showing villages in the district of Hoima and Kabale. But whenever he brought the data in, it just never showed up. So let's check some things about the data frame. Right-click Properties. And we'll go to Coordinate Systems. ARC 1960 UTM Zone 36 North. Okay, that's a pretty standard coordinate system for that area, you know, when I've worked in different projects there. Let's check transformations. So it is showing us a transformation I set before. Let's just close it. We don't need this anymore. But this is ARC 1960 to WGS 1984 option 2. And again, from working in this area, I know that's the standard transformation. So everything there looks good. Let's move a little closer to our area of interest. So we'll kind of zoom into the Hoima district. And let me bring in the data. So I'm going to click Add Data. And in this case, we're going to Folders, going to Uganda, going to Meg. So Meg is the name of the person who put this data together. And I'll select Hoima Villages, say OK. And it shows up. Let's change the color because it's picking up the same base color of everything else. Oh, I don't see it. Right click, zoom to layer. Shifts a little bit, but you know, I don't see it. If you bring it into an empty map, let's just show that real quick. Insert, new map. I'm actually going to remove the base layer. Go back to map, go to add data. Hoima Villages. So this is a new empty map with nothing in it. You would think it would show up, but it doesn't. Does it? Now, ArcMap used to give you a warning and it says this data does not fit in the coordinate system you say it's in. You know? So, but with Arc Pro, you have to do a little more work. So let's go back to our Uganda map. Let's go to Hoima Villages. And let's go in and go to Properties. Go to Source. Go to Extent. And just look at the extent of the data. Well, the top says 10 million, 205,000, yada, yada, yada. The bottom is 10 million, 118,000, yada, yada, yada. Oh, wait a minute. Here's the equator. If we're in UTM North, this is 0. I can't imagine that this is 10 million meters north of the equator. And let's try something. Got to cancel this out. And let's go. And we'll go into meters And now that I'm meters, I'm going to measure. I'm going to get to the lowest point of the Hoima district, and it's 114,000 versus 10 million something. And if I go to the northmost, it's about 201,000 versus 10,201,000. So what that tells me is that this data was probably created in a UTM south zone that had a false northing of 10 million. That explains the difference in the coordinates I'm seeing now, the value of the coordinates I'm seeing now for the northing values versus the values shown in the extent here. So this is where we're going to use, let's see if I can, oops. Let's see. I'm sorry, I'm trying to see if I can. Okay. Okay. Yeah, I was trying to clear the little box that shows who's attending because it kind of sits right on top of whatever I'm doing. I think maybe what I'll need to do is just make my map a little smaller. Okay. So what I'm going to do is, this is where I can use define projection. So I clicked into the command search, brings up my recently used, and define projection. And actually, let me do one more step first really quick. So I want to go to view, catalog pane, go to Meg, and I want to make a copy of my Hoima villages. And then we'll go right click, paste. Okay. And I'm going to work with Hoima villages 1. I'll just drag this into my map. Okay. So now let's go back to define. It's always good to work on a copy. And so we're going to go Hoima villages 1. We'll change that 1. And the coordinate system, we want to go to projected. Let's start. So we're going to projected because it is a projected coordinate system. We want to go to UTM. And it's WGS 84. So I'm looking at, basically the specifications for Hoima villages. And boy, I don't know why all of these are stretched out. Okay, WGS 84, Southern Hemisphere, and we're 36 south. Okay. And I'll say okay, and I'll run. And boom, dropped right in place. Okay, so this was somewhere along the line, the name for the coordinate system was wrong. So maybe Meg was working in something in a map that already had a coordinate system defined with the 10,000, 10 million false northing. Maybe something else was going on. Okay. Or maybe she thought, oh, we're north of the equator, so therefore it really needs to be, UTM zone 36 north. Okay. Can't tell. But anyways, the fact that when I looked at the coordinate values for the northing, there was a 10 million value difference. That gave me a clue as to what the error was. Now, it came in, but it's not quite right. So let's go back to the data frame, right-click Properties, and this is the correct transformation for that area. But let's just see what happens if we say do not transform, and we'll say OK, and boom, all lines up. I think we'll probably find a few differences, but it's all set. So it looks like when Meg made the data, she was probably working in or working on a map that was in UTM North with a 10 million north, so use 10 million false northing or some variation thereof, and that had a transformation set already. So when I brought this data in, or when I redefined it, and ArcGIS brought it in and applied the transformation, the ARC 1960, WGS 80, WGS 1984-2, it basically transformed a transformation. And once I removed the transformation, then everything lined up. So that's that. I think I'm running a little bit behind, but I think we've got enough time for one more demo. So we're going to go over to vulture analysis. So the scenario here is this researcher was studying vulture migration from Mongolia to South Korea. And so the yellow are all the GPS points or the tracking points she has. I did call out the northwestmost and the southeastmost separately so I could zoom in on them. And what's happening is she wants to use another program that analyzes or creates a matrix distance between all these points, but it has to be projected. It has to be projected flat. So probably there's programs now that would deal with it in the geographic coordinate system. But here's our problem. We need to recreate or create a new coordinate system that is as close as possible to having the same distance between these 2 points. So let's go back, map, measure distance. We'll go geodesic, and we'll go imperial, no, excuse me, kilometers. And we'll close the box. Okay. Now that I've made my screen smaller, I got to keep moving stuff around. Anyways, we'll go to the northwest vulture point, and then we'll come down and we'll make sure we're snapping to the southeast vulture point. So I already made the snaps set, and we got 2,322 kilometers. And also notice that the line between these is kind of curved, like it's going across the earth. Okay, let's make this a little smaller. And let's go and make some changes. So I'm going to right-click vulture analysis, go to properties, coordinate systems, and we're in WGS 84. Transformation, no transformation required because everything is in the same coordinate system. Okay. But I want to pick a projected coordinate system. So I'm going to go projected, continental. Now I'm just making good guesses. You know, okay, continental makes sense. Well, definitely Asia makes sense. Let's see what our choice is. Asia Lambert conformal. Yeah. Asia North. Well, that's good, but it's equal area. Asia North equidistant. Oh, we're working with distance. So this is obviously the one I want to start with. So I'll click and I'll say OK. And you can see how the map has shifted some. And let's do a measure. So I'm going to click on measure, but we're going to change to planar, and we'll use kilometers, and we'll click on the northwest vulture point, and we'll click on, make sure I'm in southeast vulture point, 2,199 kilometers. So we're 123 kilometers off. Doing the math in my head. So let's see if we can do better. And I think we can. So I'm going to right click, data frame, properties, coordinate system. And I'm going to take Asia North equidistant conic. I'm going to right click, go copy and modify. And it gives me this coordinate system here. The first thing you do, the very first thing you do when you modify, give it a different name. Okay? You don't want to overwrite an existing coordinate system. You're making a custom coordinate system. So, so I'm going to save this, come back to it in a second, and I want to go to good vultures, right click, properties. One thing I forgot to show, under source, we'll go to extent, and the top is at almost 49 degrees north. The bottom is almost 35 degrees north. The left is 106 degrees. To the left is 106 degrees. So over here, about 106. And to the right, it's almost 130. I'm going to say 129 degrees, somewhere over here. So that's the extent. That's our box. And that's what I want to try and match. So I'm going to say, OK, here, go right click, properties, right click on the data frame properties, go to, shoot. OK. I was hoping that, well, let's see. OK. We'll just start again from here. Right click, copy and modify. Oops. I'm just going to go really quick and call it vultures 2. Now, I'm going to come over here. Now, the central meridian is 95, but we know we range from 106 to 129. So I take 106, subtract it from 129, that gives me 23. I actually have this written out, but pretend I'm doing it in my head. And half of 23 is 11.5, added to 106 would give me a center of 117.5. So we want to set our central meridian to be in the center of our data. So 117.5, whoops. Okay. Standard parallel 1. So that's at the bottom in this case. And the bottom was just about 35 degrees. But this is a conic projection, kind of like that dunce cap. And the standard parallels are usually a little bit inside our area of interest. So I'm going to make this, instead of 35 right at the bottom, I'm going to make my standard parallel 1 38. Standard parallel 2, okay, that was about 49. So I'm going to subtract 3 to basically move that standard parallel inside, and we'll make it 68. Oops. Okay. And latitude of origin, whoops. Whoops. Boy. Maybe I need a little more coffee here. No, 48. So no, 46, excuse me. Okay. So 49 was about the top. I'm going to take off 3. So that's going to make it about 46. Okay. And then latitude of origin, well, that's down here. 30 works, but since we're really interested in this being our southernmost point, let's just make that 32. Okay. So in other words, I'm making a nice tight box. And let's click on save. And let's click apply. And let's close this. And let's go back to measure and planar, because we are working flat, so we want to stick to planar. Northwest vulture point, and then we snap to southeast vulture point, 2,322.33. And we were 2,322.50 before. So I think that's pretty darn close, okay, as they say. So basically, I was able to design a coordinate system that made a tight box around our area of interest, and we're getting the same distance values that we were getting from when we were in WGS 1984, when we were in geodesic. So this is, pretty good. Considering that, these values are tracking, we probably could have been off. The values we have for all the vultures are from, tracking collars or GPS. We probably could have been off 10 kilometers and still would have been good enough for purposes of our study. But again, once you know how the coordinate systems work, how these tools work, the different parameters and stuff, you can pretty much do anything. You can understand where you're running into problems. You can understand how to create a custom coordinate system. So it can be pretty good. And the key is in your own area, understanding the coordinate systems and the datums that are used in your area and kind of the specifications for them. And then also being able to basically go in to properties, spatial extent, spatial reference, look at the details, and knowing what all these values are. So I guess any questions in the last, what do we got? 12 minutes, I think. No questions?
Does anyone have any questions?
I'm gonna close ArcMap anyways. So anyways, if you I'm going to unshare. Whoops, yeah. I'm going to stop sharing, and I'll go into chat, and I'm just putting in. I'll just put in my email, and if you do have some questions, then just let me know.
So there's a comment from Mervyn, and he has said now that the latest version of ArcGIS Pro will exclude the base map when choosing transformation, and I think that's quite a nice improvement.
That is very big, because Mervyn was the one that told me about that, because I was saying, well, what's going on? How come it's not quite right? And that really makes a lot of sense, okay? And I purposely did not update to the latest version of Pro, because I'm always a little leery if I'm getting ready to do a presentation or something of not updating, a week or two beforehand. That's very important. I will go and change or make a note in my PowerPoint to reflect that. And everyone's getting a copy of this and everything. So
So I have already
Oh,
emailed a copy of your presentation to everyone that registered. So thank you for that. I'd like to just share a screen.
sure.
This is a project. It's called Correct the Map,
Ooh,
and it's just showing the different sizes globally of different countries and continents. So the blue outline is the Mercator projection that's normally used on all the maps, and the red one is the Equal Earth projection, where area now becomes important. And I think it's quite interesting because you can see how big Greenland is, how big Canada is, how big Russia is. Because on the previous maps, it always used to make Africa look really tiny,
yeah,
and not sort of like have significance in terms of area on a global scale. However, when you change map projection, you can just see how different Africa is actually quite a big place. So I'm
yeah,
hoping that this just helps to show how choosing your projection and the feature you want to show, whether it be area or direction, is so critically important. So I just think it's quite a nice graphic to show. Africa is
yes.
actually quite a big place.
Yeah, let me make a note about this. Um, and again, if you can send me to the link for this, I'd love it because I would put this in the presentation. But we had a right-wing government under a former actor called Ronald Reagan. He was actually sane compared to what we have now, but he would talk about Russia, the evil empire, using that Mercator map, which made Russia look so much larger than it is. So yeah, map projections can be really political. I think that's a really cool thing that you just showed.
So I've put the link for Correct the Map in the chat, but I will also email that to you, John.
Okay.
Last chance for any questions. A comment from Jackie. Thank you so much. This has been extremely informative for me and for a novice like me. You're welcome.
Yeah. And like I said, when I put this together, at that point, 1994, 95, I was a novice. And you just did not have the practical information that I needed. So thank you, Jackie. Okay.
And Christy, also, thank you, so useful. So John, I'd really like to just thank you so much for your time and getting up so early to come and talk to us. We're all about to start our weekend and have our first drinks. So thank you very much for your time. It's greatly
Well,
appreciated. This has been recorded and we will put it on the LinkedIn site. And I think if you registered, you will automatically get a copy of the recording. Just remember, I started the recording 15 minutes early. So just fast forward when you get the recording. The ones we post on LinkedIn will be trimmed. I think you'll automatically get the recorded one. So just fast forward the first 15 minutes. But John,
okay.
thank you for your time.
Yeah, and
So
can you?
enlightening as always.
Yeah, it's kind of fun. I'm supposed to be retired. I think I retired about 10 years ago, but actually, I was meeting some friends, new guy I met, and he said, "Well, how do you handle retirement?" I said, "Oh, I'm enjoying it. I'm great." He went out for an errand. I got your email. He came back half an hour later. Said, "Well, I'm unretired. I got to do another presentation." But thanks for the opportunity. I appreciate it. Okay.
Well, I'm sure we're going to ask you to come back and chat to us again because it's so useful.
Okay. So see you all.
All right.
Thanks a lot.
Thanks very much. Thank you, everyone.
Okay.
Have a wonderful weekend.
Yeah.
Goodbye.